Dear students, very good evening, Germany and Sri Lanka, and very good morning, New Zealand. And you all welcome to the Astro Week Eco Astronomy Inc. International Lecture Series and Online Certificate Program 2025. This is day 5, evening discussions for the South Asian region. Let's dive through some amazing discussions relevant to the material samples for Emirates Lunar missions and space industry. For these discussions, one of our talented scientists have been joining us. Warmly welcome Dr. Laura Borella, Work Package Manager at SES for the European Space Agency Academy Experiment Program. Here, a very brief intro about today's our guest speaker. Dr. Laura Borella is an accomplished young scientist and one of the few individuals worldwide to have experienced zero gravity. She holds a master's degree from the Technical University of the Berlin and has contributed her expertise to the German Aerospace Agency for over a year. During her tenure at the DLR, she worked in system engineering department supporting a critical missions such as Martian Moon explorations and the reusability flight experiment called ReFEx. Dr. Laura led a feasibility study for the gravimeter, now under review for the patent qualification, and played an active role in MMX rovers mock-up structural testing at the landing and mobility test facility, as well as flight termination systems for the ReFEx. She later earned her Ph.D. at the Microgravity Research Center in Brussels, where she participated for parabolic flight campaigns. Her doctoral research focused on developing insulating material using in-situ resources utilization for lunar application with the goal of creating thermal protecting shield for rovers. Currently, Dr. Laura Borella serves as a work package manager at SES for the European Space Agency Academy Experiment Program. Since 2020, she has also a very active member of the Eco Astronomy Inc platform. With that being said, I would like to invite this glorious and very talented, inspiring scientist, Dr. Laura Borella, to address Eco Astronomy Inc platform. Laura, it's your time. You can get started.
Thank you. Such a very nice presentation. I even look important with that. So let me, well, nice to meet you all, first of all. For a PhD or you're writing a thesis, bachelor or master thesis, may this also help you maybe to find the right direction or the right structure to go through your scientific experiment or in general through your project. So during the PhD, as it was already presented, I was developing these materials with simulant lunar regolith, which goes under the name of In-Situ Resources Utilization. And then the purpose of developing these materials was to monitor, basically, thanks to the participation with the Emirates Lunar mission, the degradation over time or the impact that an environment such as the Moon environment had on the materials in itself. So the agenda of the day is going to have a project introduction, the objectives of my research, the methodology that I implemented, the development of these materials and their synthesis, the characterization and test, and a bit of image analysis, which was the way basically to understand how regolith and especially what regolith could do on the materials to extrapolate some scientific results. Then, of course, presenting the results and a little bit of a future perspective for the thesis that I did. I want to start with this very famous quote by Neil Armstrong. One small step for a man, a giant leap for mankind. Why? Because every research, every little piece of contribution that we develop and we give to society is something that helps everyone, and not only you to achieve your personal goals, but also humanity in general. As there is progress, there is investment in research and development of new technologies, which help humans to live a better life and to improve the current conditions. So the missions on the Moon. So always landing on the Moon has been quite difficult. Maybe this slide is not entirely up to date, since recently there's been more landing on the Moon. one also from India, which is extremely successful. I'm a big fan of the Chandrayaan missions. But 23, let's say, right now landed successfully on the moon surface. Do you know how many tried to land on the moon surface? No? Well, 152 missions were launched, but only 23 actually succeeded to arrive on the moon. And why is that? Because it's a very difficult environment. Here, I just wanted to give an overview of some of the missions that were able to make it until there. And then the benefits of doing this is because, as I was mentioning before, it's improving Earth life, not only research in space for space exploration, but the benefits always are reflected on Earth. For example, did you know that from the main missions, there has been a lot of technologies developed that then were used also for Earth applications, such as the mattresses in which we sleep every night, the solar panels, the fireproof firefighters uniforms, the advanced cameras, also the thermal blanket when, for instance, you have an emergency and the ambulance comes. So these are all technologies right now largely widely used on Earth. That actually come from space research. Why? Because they were first developed to survive or to help astronauts or even unmanned space vehicles, so rovers, satellites, and so on, to survive the space environment. Right now, moon exploration is definitely one of the hot topics, let's say, in among all the agencies, and the idea is to develop a moon base. And this that you see here is maybe a little bit utopic right now. We are not so close to develop this structure, but that's the goal from all the space agencies. These are just domes, basically made of materials of any kind, and inside these domes there's supposed to be laboratories, a little bit like it's on the ISS, the International Space Station. It's an orbiting station in which astronauts inside operate experiments that us researchers on Earth develop. And that is going to be the same also for the moon. But why didn't we build these moon structures yet? Why weren't we able to land successfully on the moon surface? Well, the answer is very easy. It's because there's a very harsh environmental conditions. So this is the moon, clearly, as you can see, and the moon surface. One of these harsh conditions, it's really is coming, from the moon surface. The moon surface is covered with the regolith, which is a sort of sand that has, as you can see here, a different type of shapes. It's a fine-grained soils, but also there are some breccias and some rock fragments. If you look at a little bit on the microscope, you can actually notice the morphology of this grain, which is extremely edgy. I don't know if you can see my screen, my mouse right now with the indicator, but all these rough edges here, and these are extremely abrasive for the materials, which makes very difficult to them to survive. Here, another example of whatever it was found, these rocks that were found on the moon. On top of the lunar regolith, which is already complicated to deal with, there are also the environmental challenges coming from the temperatures. A lunar day is more or less 14.5 Earth days, and the same is for the lunar night. But the temperatures, they go up to 123 degrees Celsius during the lunar day, but during the lunar night, they can drop up to minus 173. It's super cold. And when we can protect, let's say, our rovers from very hot temperatures, it's more complicated to protect the rovers or any kind of project that costs a fortune, obviously, from the very cold temperatures. The main reason is because electronics right now, with the current knowledge that we have, cannot withstand such kind of cold and harsh temperatures. And so this beautiful rover here, unfortunately, is going to die if we're not going to protect it in a way. Together with this, there is also a bombardment of galactic cosmic rays and solar charged particles that hit basically the material surface. This is a picture from Perseverance rover, which landed on Mars, and you can see the holes already created on the wheels. It's clear, it's visible, and this is what is going to stop at a certain point the mission. Because the regolith contains also metal particles inside, then the charged particle combined with the metals, this also generates a sort of magnetic field, a local magnetic field, which makes the whole situation even more complicated. And this is the result basically that we're going to see after a certain amount of time, which is not that much actually. 10 days, it's already something. Moreover, because of that, the fine soil particles gets extremely attached, adherent to any kind of surface. When it's a meta surface of an unmanned space vehicles, we care about the mission, so there's not going to end. But when we have astronauts, these particles are actually cancerogenous. So we need to pay a lot of attention. And I read some papers in which there's a testimony of an astronaut indeed who went to the moon from the Apollo missions, and he said that once he was back in his capsule, the regolith attached to his suit was so strong that he could barely see or he could barely breathe inside the capsule. So what do we need to do that? At least for the protection of the astronauts, but especially to be able to build those very nice structures that we saw in the beginning. I would say, this is my personal opinion, that the first thing we need is materials that can degrade less and they do not create harm for astronauts or our missions. During the PhD, as I was mentioning, I participated in this Emirates Lunar mission, and the goal of the PhD was exactly this: to create materials, potentially also utilizing regolith. So one day they can be produced directly on the moon and not on Earth. So this way we reduce the cost of launch and the weight, obviously. And these materials were supposed to be attached to the rover's wheel. This is the rover developed by Mohammed bin Rashid Space Center in Dubai. The mission was launched on the 11th December 2022, and then unfortunately there was an attempt of landing 25 April 2023 due to a fault of the lander. The rover didn't make it successfully on the moon. But in terms of research and development, I would say that it was still a good result, at least for me and my PhD, let's say. This was an example of the trajectory that the lander had to go from Earth to reach the moon. And as I was mentioning, so these materials were attached here on the rover's wheels within the grousers. So each material, while the rover was navigating on the moon surface, would have interact with the lunar soil, and then from that accumulating or repelling lunar regolith and interacted with the harsh environment that I just explained. During the PhD, I had also the pleasure of managing a consortium with a few entities, few institutions involved. But of course, the collaboration with all the scientific partners was much wider. And we had, of course, Mohammed bin Rashid Space Center, who developed the Borella rover. We had ETH, which is another university in Zurich, doing other samples of materials, Airbus, MIT, and many others. Here it's in blue, it's ULB, so it's the university where I did my PhD. Thanks to international collaborations, of course, the outcome of the scientific results would have been maximized. We have in ULB, yes, as I was saying before, I was managing also this consortium within the University of Cambridge, York in Canada, and ESA. The samples of materials that were launched were exactly this one from the ULB side. So I will summarize it a bit here. Maybe it's a bit too complicated. However, one type of materials were aerogels based. You know what is an aerogel? You can say yes or no. I'm not. I guess you don't, maybe. Well, for those who don't know, an aerogel is a porous material which helps for thermal insulation, because indeed we want to protect from the temperatures that I was mentioning before. These aerogels had the particularity of being with the simulant lunar regolith, so trying to enable one day the production of these materials on the moon directly. And then the second big family of materials were PDMS, polydimethylsiloxane. It took me a while to remember the name, so don't worry if you don't remember it. But that's an organic silicon, and white silicon because it has been proven that water-like materials are, or water in general, it's the most effective material to use for radiation shielding. The purpose, so the scientific objectives were all the same, so to study this temperature range, material degradation, scratching, so every type of abrasion on the material, and additional repulsion of the lunar regolith. Sorry. There was also research about the glue, because these materials, how do we attach them on the grounders? So the materials had to be attached with certain glue, space qualified, that we knew could withstand the temperatures, but especially creating an adherence with the material we were looking at. So one of the most used glue in space, which is this Scotch Weld epoxy adhesive 2216, was not good enough for the PDMS type. So we have to change and find another one. Here is an overview of the materials that ESA proposed, and then we have another overview of the other materials that the University of York proposed. So to enable space exploration, which kind of characteristics are we looking for? We're looking for easy material casting, so we need to produce it in an easy way. We need them to use also in-situ resource utilization. We need to study this additional repulsion lunar regolith, and of course it must have lightweight properties. Why? Because we have limited equipment in space, we have limited resources, we have abrasion of the materials, and we need to reduce the launch cost. So in general, when we look at the material selection, we need first to do a lot of literature research and see how these materials are characterized, let's say, in a way. So we need to translate the function to see what they are for, what they're built for, select the objectives. We need to look at the shapes, so we need to look at the process also on how to make them and the type of material that we involve to make the final product. So what I did is I started from my objective to find novel materials for moon missions. Then I identified the constraints, and these are just a few, but it's the most surprising ones. Then we went through the literature research, so state-of-the-art, material selections, so what is already done, not what you propose new. And then the key parameters that we need to identify. And we went through once we develop the new material, we go through the characterization. So we need to know through the characterization how these materials can be located, let's say, in a certain chart, and how we could expect them to behave. So for this, there is material synthesis and the property identifications. Testing, of course, we need to do tests to verify if it can work or not. And then the analysis and the post-processing of the results. So the key parameter right now are those mentioned here. Given the constraints, which are weight, ionized radiation, thermal stability, thermal insulation, and debris impacts, we needed to identify the density and the structural uniformity. You don't want a material that is not uniform, because this can create points of failures that you don't want to go through. Radiation shielding, resistance to deformation under heat loads. We need to understand the Young modulus, which is something giving you the hardness, the strength of the material. Low thermal conductivity, additional repulsion of the regolith, as I've mentioned quite a few times, and then we will see why, and the use of this in-situ resources utilization. So this graph comes from very well-known software, but also in books, and it puts in correlation the density of the materials in the Young modulus. So all the materials we know, they are in this graph. And then from this, we need to understand where to locate our materials. So ideally, for space, to reflect the low density and the Young modulus parameters, again from the literature research, we need to be located in this area circled in red. For this selection, so I was thinking at the time, let's use aerogels because they are lightweight and all the parameters I mentioned before, and using them, they're similar to lunar regolith. These in the pictures are actually the materials I developed. So if we look at this one here on the bottom left, the white one is just a simple aerogel. And then we have 20% of concentration of simulant to lunar regolith, 40% and 60%. Respectively. I also cast the material in different shapes. As you see here, there is an hexagon, but there are also tiles. There is a pentagon as well. And as well, I was able to cast, it was a little bit more tricky and with the specific techniques. But a mold, so I casted a mold for battery insulation. And of course, this is just easy, let's say, proof. It was not tested to the extent to verify how well this is working or not. Then the other family of materials that I developed is PDMS with carbon nanotubes and graphene. Why? Because it has been proven from literature research that graphene has radiation shielding properties. To identify this, I developed the materials in a way in which there was a certain surface pattern. Here you can see some spikes with a square shape. Because then when analyzing the results, I should have been able to monitor what it is the adhesion or repulsion of the lunar regolith. So if you identify how much regolith is increasing the materials, you can give, let's say, a rough estimation of the area of the sample that is covered or not with this regolith. These are all the type of tests that I conducted to characterize the materials for the porous, the chemical bonds, amorphous behavior or not, the thermal, and so on and so forth. Again, now going back to the original methodology, since we completed the characterization, I then went through the testing. So the materials here is these are the pictures actually of the flight model materials that are now on the moon, and they were attached to the rover's wheels. The materials were mounted here. So you see it's within the grousers. The wheel here containing the materials on the center pictures was going through the regolith path. And after a few rounds, or already from the first one, the collected regolith from the material is what you see on the bottom right picture. Every material was very light. It's less than 3 grams. And the dimensions were 30 by 70 centimeters. During this navigation, a way that we had to monitor the additional repulsion of these materials is simply to take some pictures. And then for this reason, in the picture, so this is, as you can see, the ground test that I performed during my time at the Mohammed bin Rashid Space Center using the engineering qualified model of the rover. We take the pictures and then we analyze the results. How do we analyze results for pictures? Well, we need then to, we also tested the different light conditions to make sure that our results were coherent. And we then go through the image analysis, basically, that was my second part of the PhD. We start taking ground zero pictures. So these are our reference. And then we take the same picture, doing the same path back and forth, putting an illumination condition coming from ground left, one coming from the top, and then another one coming from the ground right, and then on the top right. And you can see already like the very different type of pictures. Why is also that important? Because while you are analyzing the images, you need to understand that you have to be the same condition because it's based on pixel intensity. So there are some light interactions, let's say, with the camera that gives you false positive or false negative. In fact, if you look at the up left, this picture seems taken in a completely different environment, and no, it's not. But if we want to maximize then the results that you have from your analysis, you for sure need to take it on the ground left. And that was exactly the potential direction of light if the rover would have navigated actually on the moon surface. Image analysis. So what is image analysis? This is a methodology, is a technique used to extrapolate results from an image. And for what I needed to do, I used the two algorithms, which are kind of easily implementable. The first one is called the watershed segmentation. So it was dividing the image in segments, but we will go later. And the second one, it was using structural similarity index. That gives you a percentage of how much the two pictures are actually similar or not. For the So for the structural similarity index, this was basically the roadmap to follow. So I produced this code. These are examples of the two pictures. You import the pictures into the software, then you convert it to grayscale, and then you find the key points and descriptors, and then you match basically this part, and through the analysis, all these dots that you see here, identify the common points that you have between the two pictures. The result is that these two pictures are 35% similar to each other. And the result is exactly written here. It's a screenshot from my script. Then the second one that I used following the logic is the watershed segmentation. And this was actually also used to characterize some of my materials, the aerogels. So the pictures on the top one, it's an image taken with a very dedicated microscope to identify the porous. So in this software, in this microscope, sorry, you can also identify the diameter of the porous, because it's capabilities of the software in itself. Here, for example, is in microns. But if we want to achieve the same one, the same result, let's say with image analysis, then we run the algorithm that you see here, and then it's not super visible from the picture. But then I try to highlight it using different colors on image 3 here on the bottom, and these are the porous identified within the structure. Let's say this was a trial, because this picture in particular, so porous materials, is not easy to analyze, since the structure in itself is in 3 dimensions, and this software works in 2 dimensions. So whereas sometimes there is something similar to a structure, in reality is actually a hole. So these are increase the porosity, which is one of the characteristics of the materials, quite consistently. But if we run it in other type of materials, for example, these ones, the PDMS, here you see from the different paths. So from the different, same light condition, different light conditions, same sample that went through the regolith flat during the testing several times. And then the algorithm, as you see, identifies the regions, the segments, that's why the name segmentation, the segments in which the regolith is attached. And here we have much more accuracy, actually. Sorry. The result is this pattern, basically, that you can extrapolate from the values of the software, in which you can see that for some of the sample, from the beginning to the end, it stays quite the same, and for others, it actually decreases. So it's less similar to the first one, which means it's going to add more regolith, it's adhered on the sample. We run the same algorithm basically for all the different light conditions, and here I divided the results based on the region. If we, as I was mentioning before, if we want to run the analysis to measure the porosity, or to estimate actually the porosity of the samples, then this is what you can extrapolate, which is a very nice graph. So we start from the pictures I was showing you before. Here there are also the diameters of some porous indicated. Then for the three samples with different concentration of regolith. And then based on the diagram that I showed you before on the porous analysis, again, as I was mentioning, we can extrapolate the area of those porous. As you can see, aerogels with 60% of regolith, if you know how to read the graph, has a very big spike here. Why is that? Because if I look at the picture, you see 1, 2, 3, 4, 5. There's plenty of small porous. While if you decrease the regolith inside the aerogels, then the porous diameter becomes bigger. Here we go to 34 micrometers, and here we have 100 micrometers. So that was one of the results that I was able to prove during the thesis, and I got on a publication as well. But out of all this material, basically, who's the winner? So we go to the literature research I was mentioning before, and that's how you can prove your results, you can prove your research. So you start from something in the literature, you find the gap, you develop your own solution, let's say, to fill that gap, and then you place it in the literature to give your contribution. And that's exactly, again, in the same graph, where aerogels with simulant lunar regolith and the PDMS-based materials would have been located. I also measured the thermal conductivity and some thermal properties. And again, that was an easy test, let's say, because it was just an instrument that was able to identify the properties. However, again, I took these results and I put it inside the diffusion research I was looking at in the very beginning. Conclusion, what can we say? Aerogels, they reflect exactly what we were looking for before. Density, in terms of low thermal conductivity, in terms of the resources that we could use in situ potentially, and the additional repulsion of the lunar regolith. Both family of materials share the structural uniformity, which is very important. So I demonstrated with these slides my objectives that I showed in the beginning of the presentation. And for the PDMS, we have a Young modulus, coherent with our research, potential radiation shielding properties, and the resistance also to deformation under heat load. Perspective, what can we do from here? So you will not create the perfect material at the end of a PhD, or maybe you will. I was not that genius probably, but just with the identification of my research, I can totally say that whoever is going to take this as a follow-up, and there's a colleague of mine actually working on this as part of his PhD at the same university. We need to improve the thermal stability of the aerogel. We need also to treat the hydrophobic behavior. We need to do space environmental tests. So just the ground tests are not sufficient to determine all the objectives. Then we need to combine maybe layers of these materials together to have a unique composite sample to perform way better. Then there is of course some refinement on the image analysis algorithm that I've done, and probably use some other algorithms for a better overview or a better use of this analysis. So at the end, I have to say that this was a small step for humankind, actually, but it was a giant leap for my PhD, and I was happy to work on this mission and having this journey. I conclude my presentation then with this last picture, which is me and my colleagues in Dubai when we were having meetings, and also a little bit of fun, I have to say, outside our working hours. Yeah, thank you very much for your attention. I'm happy to take any questions.